All right, let's put what we've learned in this unit to our last goal and apply it. So what holds different types of crystals together? So when you look at a metal substance or an ionic substance or a covalent substance, what is holding those together? And we've talked about all of these, so this should all be review. We are also going to learn about network solids, which is our new material for this goal. So what holds metals together? Metallic bonds. What holds an ionic solid together? Ionic bonds. What holds covalent solids together? Intermolecular forces. So notice the covalent molecules are held together with these van der Waals forces, the dispersion, dipole-dipole, hydrogen bonding, which are a lot weaker than how the molecule gets put together. And then we're going to talk about, as I've already said, this new substance called network solids. They are held together by covalent bonds. So they're just a giant, massive molecule. And a good example of a network solid is a diamond. When we look at crystals, crystals have unit cells. This is a 3D arrangement of the atoms, the molecules, or the ions, and it's what makes up the crystal. It's a building block, so to speak. And then let's look at a crystal lattice. A lattice are these unit cells put together. A good analogy of this is Lego bricks. If you have one Lego brick, that is like a unit cell. And if you take those Lego bricks and you build a wall structure, that would be a lattice of those unit cells. And there's very many different types of unit cells, and it's not necessary for you to learn these or study these unless you have an interest in it. I'm not going to be testing on the types of unit cells. It is very interesting, though, how these crystals are put together. If you look on the back of your white periodic table that I gave you at the beginning of the year, there's a little legend that shows what every element, what their unit cell is when they're put together. So these crystalline shapes, they have many different shapes with different names. Again, I'm not going to be testing on this, but I do think chemistry is very beautiful. And here we can see real examples of these unit cells. So a crystal, if you leave it undisturbed and let it grow, it can reveal the unit cell. So the unit cell is a repeating pattern over and over and over again. And so you can see how this gets repeated over and over. And so you can see the unit cell in the crystal lattice. All right, metallic bonds. So a metallic bond, these are positive ions in a sea of electrons. So in the crystal, those unit cells, we will have those cations, these little positive ions. Flowing through the unit cell will be those delocalized electrons, those free electrons. In the metallic bond, metals are the way they are. They have these metallic characteristics of malleability, ductility, conductivity. They don't dissolve in water, and it's all because of their metallic bond, this electron sea model of positive ions floating in a sea of electrons. Here's just some more of their crystal lattices that you can see. All right, ionic compounds. So what holds ionic compounds together? Ionic compounds are all solids, and they are held together with cations and anions attracting each other. It's called electrostatic attraction. So in your crystal, the points of your unit cell, we will find those positive or those negative ions. This is a picture of a calcite crystal that I took at the Smithsonian Museum when I visited in 2014. This crystal, I should have put a person in front of it so you can see truly how large it is. It's about waist high, so a very, very large crystal. You can see that unit cell repeated over and over and over again. And calcite is ionically bonded with a metal cation and a nonmetal anion. Here's some more examples of some ionic compounds, their crystal structures. All right, now to covalent solids, which we spend a good portion of this unit talking about. When we look at a covalent solid, the atoms in the molecule are covalently bonded, but the molecules themselves are held together with intermolecular forces. For example, look at this dry ice. So dry ice is carbon dioxide and carbon dioxide is a linear molecule. And so the points of the crystal lattice, that is where you find these molecules. And we know that the CO2 molecule is nonpolar. So nonpolar and nonpolar, what holds it together is dispersion forces. And so we'll have dispersion forces in between these molecules. Now, if you know anything about dry ice, we know it sublimes. So if you put some dry ice on a tabletop, it will immediately turn into a gas over time. So go directly from a solid to a gas. But it's these dispersion forces that are breaking when it is going from that solid to the gas. All right, the picture on the right, this is the structure of sugar. So sugar is a covalent solid, and what holds sugar molecules together is hydrogen bonding, dipole-dipole, dispersion, all of those go through. And you can see the crystals of that sugar molecule. And again, it's the van der Waals forces and the hydrogen bonding that's holding it together. So down here, this last picture, if you look at a very, very large, or excuse me, long hydrocarbon, we find that it's nonpolar, and so only dispersion forces are holding it together. But there's so much surface area that the dispersion forces are actually quite large, and these tend to be solids. When you look at covalent solids and also their liquids held together with intermolecular forces, I have 3 examples here from the periodic table. First of all, at room temperature, we have chlorine. This one does not have uh, intermolecular forces because gases do not have forces in between them. But if you go over to bromine, bromine does have dispersion forces in between its molecules, holding it together as a liquid. And you find the same thing with iodine. You do have those dispersion forces holding it together. And chlorine also would have intermolecular forces if we could slow the molecules down. So if we get it really, really cold, we can turn that chlorine into a liquid. And then it would also have those dispersion forces. All right, our new stuff. Network covalent solids. So these are not crystals, but they're one huge molecule covalently bonded. When you compare network solids and the temperature that which they melt or boil, they're going to be much, much higher than ionic solids, and of course, much, much higher than the covalent solids, which tend to be a little bit lower than ionic. And your metals are somewhere in between your ionic and your covalent solids. So we have our network covalent solids, some examples. One example is a diamond. So when you look at a diamond, each carbon is covalently bonded to 4 other carbons. And this gives a very, very strong structure. So when those carbons bond, they're essentially making a tetrahedral with themselves. And then this will repeat over and over and over again. So again, every carbon will have 4 other carbons that it is bonded to in a tetrahedral. So kind of hard to draw out, but if you look at the model that I have right there, you can just picture this really, really strong structure. So when you go to cut a diamond, or it's hard to imagine melting it, but you would have to break those covalent bonds. Another type of network solid is graphite, and this is another form of carbon. And this carbon, instead of being bonded to 4 other carbons, it's only bonded to 3 because there ends up being a double bond in there. So it makes these sheets. So, and in these sheets, there will be some double bonds scattered so that you can see that they will all be bonded to 3 other carbons. Now, in between the sheets, we have dispersion forces. And dispersion forces, again, are what holds nonpolar to nonpolar. So although the sheets are quite strong, in between the sheets, it's very weak. And so if you ever use a graphite pencil, what you're doing is you are smearing these strong graphite sheets on your paper by just using pressure from your hand to break those dispersion forces and lay down these sheets of graphite. All right, another form of carbon are fullerenes. They are affectionately known as buckyballs. When I first started teaching chemistry, the scientists were very excited about these fullerenes, but I really haven't seen much research come from this. Instead, the research is more concentrated in these next couple. Nanotubes, if we look at those graphite sheets and we curl them up, so to speak, we can form something called a nanotube. They're super strong. They also will carry a current down through the middle of the nanotube. And again, the research is going in this direction. So all these different forms of carbon, all of these network solids, these are allotropes of carbon, or different ways that carbon can bond and form different molecules. So again, diamond, we have each carbon bonded to 4 other carbon, and then with your buckyballs and also your graphite and your nanotubes, you have each carbon bonded to 3 carbons because there's a double bond in there. All right, another form of graphite is something called graphene, which is one sheet of this graphite structure. So super strong, is still a network solid, but one sheet. And so a lot of research is going to these, hopefully because we want to make portable electronics. And I will link this video so you can watch it.